The freezing stage is complete. Inside the freeze dryer, every pharmaceutical vial now contains a completely frozen product, ready for the next stage of the process. Primary drying begins as heat is transferred into the product. Ice sublimes directly into water vapor, and that vapor is transported out of the vial. Together, heat transfer, mass transfer, and sublimation determine the success of primary drying. Primary drying begins with a product that is completely frozen. The interconnected ice crystal network formed during freezing establishes the structure that will remain after drying. As energy is supplied, the ice is removed by direct sublimation, changing from solid to water vapor without passing through the liquid phase. Inside the freeze dryer, carefully controlled shelf heating and low chamber pressure maintain the conditions required for this transformation. As the ice disappears, it leaves behind a porous structure that preserves the original shape of the product and prepares it for successful reconstitution. Primary drying begins with a controlled source of heat. The temperature-controlled shelf transfers energy through the glass vial and into the frozen product. As this energy reaches the sublimation front, it provides the latent heat required for ice molecules to break free from the crystal lattice and enter the vapor phase. The energy pathway is continuous, from the shelf, through the vial, into the product, and finally to the sublimation front, where sublimation takes place. Sublimation does not occur throughout the entire product line. Instead, it occurs only at a thin, moving boundary known as the sublimation front. Above this interface is a dry, porous layer where the ice has already been removed. Below it, the product remains completely frozen. As ice sublimes, the front gradually moves downward through the vial, while the generated water vapor travels upward through the dry layer and exits the product. By the end of primary drying, the sublimation front reaches the bottom, leaving behind a completely dried, porous structure. Once the ice has sublimed, the resulting water vapor must travel through the porous dry layer before leaving the vial. This movement of water vapor through the pore network is known as mass transfer. As primary drying progresses, the dry layer becomes thicker, increasing the distance the vapor must travel. The longer and more tortuous this pathway becomes, the greater the product resistance to vapor flow. Only after passing through the porous structure does the water vapor finally leave the vial and enter the freeze dryer chamber. Successful primary drying depends on maintaining a balance between heat transfer and mass transfer. If heat enters the product faster than water vapor can escape, the product temperature rises, increasing the risk of exceeding its critical temperature. On the other hand, if too little heat is supplied, sublimation slows and the drying cycle becomes unnecessarily long. The objective is to maintain the product within a safe operating window, where heat input, vapor removal, and product temperature remain in balance, enabling efficient and reliable primary drying. The efficiency of primary drying is influenced by several process variables working together. Shelf temperature controls the energy supplied to the product, while chamber pressure drives the removal of water vapor. The ice crystal structure formed during freezing determines the pore network through which vapor travels. Fill depth, vial geometry, and product resistance all influence how easily heat enters the product and how efficiently vapor escapes. Optimizing primary drying means balancing all of these variables to achieve efficient drying while maintaining product quality and process robustness. Primary drying is typically the longest stage of the entire lyophilization cycle. Every ice crystal must receive enough energy to sublime, while the product temperature remains safely below its critical temperature. As drying progresses, ice is removed gradually, and the sublimation front continues moving toward the bottom of the vial. Simply increasing the heat is not the solution. The process must remain carefully controlled to protect product quality. The fastest primary drying cycle is one that maintains the right balance between heat transfer, mass transfer, and product temperature. Primary drying is now complete. The ice has been removed, leaving behind a stable, porous structure that preserves the product's original architecture. With the bulk water eliminated, the product is ready for the final stage of the lyophilization cycle. In the next episode, we'll explore secondary drying and discover how bound water is removed to achieve the residual moisture required for long-term stability.